Today we're peeling back the layers on a piece of critical, often unseen technology found on massive LNG carriers, the gas heater systems. They seem to go by quite a few names: HD heaters, boil-off warm-up heaters, sometimes fuel gas heaters as well.
That's right. Different names, but they essentially do a crucial job managing really extreme temperatures.
Right, bridging that gap between the super cold cryogenic cargo tanks and the warmer operational needs of the ship, like fuel for engines or preparing tanks for maintenance.
Exactly. We're talking about highly specialized equipment, usually tucked away in the cargo machinery room. They're fundamental for using the gas on board, but also, equally importantly, for safety, especially when heading into dry dock.
So our mission today is to use the technical specs we've got, from makers like DongHwa Entec or Cryostar, and really understand how these things work, from the basic engineering right down to the safety trips.
Sounds good. There's a lot packed into these units.
Okay, let's unpack this. So looking at the hardware itself, it's described as a shell and U-tube heat exchanger, which sounds, well, pretty standard in engineering terms.
It is a robust, well-understood design, yeah. Fundamentally, you have steam on one side, the shell side, and the process fluid on the other, running through those U-shaped tubes.
And that process fluid is the cold stuff.
Exactly. It's usually the cold gas, could be LNG methane vapor, might be nitrogen, or even inert gas, depending on the operation. And the steam provides the heat. We're typically talking saturated steam from the engine room, maybe around 7 bar gauge pressure, which puts it at roughly 169 degrees Celsius.
Okay, so that's the how. But why the different names? HD, warm-up, boil-off, fuel gas. Are they physically different units, or is it just what they're doing at the time?
It's mostly about the job they're doing, their operational mode. You could maybe simplify it down to two main, really critical duties.
Right. Let's maybe start with the one that sounds most safety critical, the one dealing with the really extreme cold, and I gather has some very strict limits. That would be the warm-up mode.
That's the one. The warm-up mode is all about maintenance and safety. It's used when you need to prepare those huge cargo tanks for people to go inside for inspection, or when the whole ship is going into dry dock.
Because you obviously can't have people in a tank that's at minus 160 Celsius.
Precisely. So the system takes the very cold vapor from the tanks, could be down near minus 130 C, and circulates it through the heater to warm it up. It has to be done slowly, carefully.
And this is where that really thin temperature limit comes in. The sources hammer this point home.
Absolutely. There's a non-negotiable hard ceiling. The gas temperature coming out of the heater must not, under any circumstances, exceed plus 80 degrees Celsius.
80 degrees? Why so specific? What happens if you go over?
Well, it's all about protecting the cargo piping insulation. That insulation is sophisticated stuff, often layers of polyurethane or similar foams designed for cryogenic temperatures. If you hit it with gas hotter than 80 C, you cause thermal damage, fatigue.
So it's not just melting plastic, it's actually damaging the integrity of that crucial thermal barrier around the pipes.
Exactly. You breach that limit, you drastically shorten the life of the insulation, potentially compromise the pipework itself over time. That leads to boil-off problems, safety issues, and eventually a very expensive, complex repair job in dry dock.
Okay. And because warming up those massive tanks needs a lot of heat transfer.
Right. The gas flow rate during warm-up is substantially higher than during normal operation. That's why the procedures usually demand that both available warm-up heaters are used together. It shares the load, helps maintain control, and keeps things below that critical plus 80 C.
Got it. So that's the critical safety and maintenance role. What about the other main function? How do these heaters play into actually running the ship day to day?
That's the second mode. The boil-off gas, BOG, or fuel gas mode. LNG naturally evaporates slightly in the tanks, creating boil-off gas. Instead of just venting it, modern ships use it.
As fuel.
Exactly. So in this mode, the heater takes that cold boil-off gas and warms it up. It might be feeding the gas combustion unit, or GCU, which is basically an incinerator for excess gas. Or, crucially, it could be heating the gas to be used as fuel in the ship's engines.
Like the dual fuel generator engines, the DFGEs.
Precisely. For the DFGEs, you need the gas at a specific temperature for efficient combustion. So the heater might take gas coming in around, say, minus 100 C and warm it up to somewhere between 40 and maybe 57 degrees Celsius.
Still warm, but not pushing that 80 C limit.
Correct. For the GCU, it might be heated a bit higher, maybe 60, 70 C, just to ensure stable burning. Whether it's labeled an HD heater or a specific fuel gas heater doing this job, the principle is the same. controlled heating for operational needs, avoiding damage.
Okay, here's the part that seems like a real engineering puzzle. You've got this incredibly cold gas coming in, and its temperature can fluctuate wildly, right? Maybe from negative 125 C all the way up to, I don't know, plus 20 C if the tank is nearly warm.
That's right. The inlet conditions can vary hugely.
Yet the outlet needs to be kept incredibly stable, especially for that warm-up mode, holding strictly below plus 80 C. How on earth do you manage that level of precise control with such massive input swings? It sounds like it would be impossible to do manually.
Oh, it would be completely impossible manually. The stability comes from some clever automation, specifically what's called a split-range control configuration.
Split range.
Okay.
What does that mean in practice?
It means you have one temperature controller, a standard PID loop calculating how much heating is needed, but its output signal controls two valves simultaneously and usually in opposite directions.
Okay, so one controller signal does two jobs.
Exactly. Think of it like this. One valve is on the main line into the heater tubes. Opening this valve lets more cold gas flow through the heater to get warmed by the steam.
Okay, the hot tap.
Sort of, yeah. And the other valve is on a separate bypass line. This line allows cold gas to completely skip the heater. Cold tap. That's a pretty good analogy. So if the controller sees the outlet gas temperature is too low, it starts opening the valve going into the heater and closing the bypass valve. More gas gets heated.
Makes sense.
But if the outlet temperature starts getting too high, maybe creeping up towards that dangerous plus 80 C.
It needs to cool it down fast.
Right. The controller then does the opposite. It starts closing the valve into the heater, reducing the flow getting heated, and simultaneously opens up that bypass valve.
Injecting a stream of the original cold gas back into the outlet flow.
Precisely. That direct mixing of cold, unheated bypass gas instantly pulls the final outlet temperature down. It's a very responsive system.
The documentation has this table showing the valve positions versus the controller output percentage. It shows this overlap. Like, even when the inlet valve is fully open, the bypass might still be slightly open or ready to open immediately.
Yes, that overlap in the middle range is key. It's not always just one valve fully open and the other fully closed. In that middle control band, say between 40% and 60% controller output, both valves might be partially open, constantly fine-tuning the mix of heated gas and cold bypass gas.
So it's constantly balancing the two streams.
That's the elegance of it. It ensures stability because you always have that cold bypass flow available instantly if the temperature starts to overshoot. It provides very tight, stable control despite those wild inlet swings.
Okay, that makes the control aspect clearer. Now, shifting from design to actually using this kit, the operating procedures you find are incredibly specific, especially about the environment these heaters are in the cargo machinery room. What are the absolute must-dos before you even think about letting steam or cold gas near these things?
Safety first, always. The cargo machinery room is a hazardous zone by definition because you're dealing with methane piping. So before any operation involving LNG or natural gas vapor flow in that space, two systems absolutely must be running. First, the cargo machinery room exhaust ventilation fans, high-capacity fans constantly changing the air.
For dilution, presumably, in case of leaks.
Exactly. Dilution is the first line of defense. If there's a minor flange leak, the ventilation helps keep the gas concentration way below flammable limits. Second, the gas sampling system must be active and monitoring.
Continuous detection.
Right. These are fixed sensors sampling the atmosphere at various points. They provide the early warning if any gas is present. You absolutely have to establish environmental safety, ventilation, and detection before you introduce the process fluids.
Okay, environment secured. Then comes the actual startup. There's a very specific procedure about preheating with steam before any cold gas is introduced. It says the heater needs to be warmed until the condensate outlet is hot, maybe 100 C or even 170 C.
Why is this step so critical? What are we preventing?
We're preventing catastrophic thermal shock. Imagine hitting cold metal, maybe ambient temperature, say plus 20 C, with gas that's suddenly at minus 125 C.
Yeah, that sounds violent. It is. For the metal, especially the carbon steel shell and the U-tubes, that instantaneous massive temperature drop causes huge internal stresses. It can make the metal brittle, lead to stress cracking, and basically cause the tubes to fail almost immediately.
And a tube failure means?
It means high-pressure, cold gas leaking directly into the steam side of the system. A major failure, requiring immediate shutdown and likely a very difficult, expensive repair, probably replacing the whole tube bundle in dry dock.
So the preheating avoids that sudden shock.
Absolutely. The procedure is to slowly introduce steam first. You crack open a small warming bypass valve, vent the air out of the steam side, and let the entire unit gradually come up to steam temperature. Only when the whole thing is properly hot, confirmed by the condensate temperature, is it safe to start introducing the cold process gas. It's a non-negotiable step for equipment, longevity, and safety.
Right. Once it's running, heating gas with steam, you generate hot water condensate.
Yeah.
The system for handling this seems quite involved too. It goes through a cooler, then into a special gas vent drains tank with baffles and weirs inside. Seems complex just for draining water.
But it's not just about draining water. That condensate system is actually another clever integrated safety loop. It's the primary way the system detects if one of those U-tubes has failed during operation.
How so?
If a tube cracks or develops a leak, what happens? Cold methane vapor under pressure will immediately start leaking into the steam condensate side.
Okay.
That special brains tank, with its internal baffles and weir plate, is designed to act like a separator. It slows the flow, increases the surface area. Basically, it encourages any dissolved or entrained gas bubbles in the condensate to break out.
To come at a solution.
Exactly. And where does that separated gas go? The tank has a vent line.
And where does the vent line lead? Let me guess. Back to the gas detection system.
Straight back to the gas sampling system. So if the detectors pick up methane in the vent line from the condensate drains tank, it's an immediate alarm. It tells you you've got a tube rupture inside the heater.
And that stops potentially gassy condensate getting pumped back to the boiler feed system in the engine room.
Precisely. It prevents a potentially explosive situation in the engine room by detecting the leak right at the source in the cargo area. It's a really neat piece of integrated safety design.
Okay, let's talk about stopping. What's the difference between a planned, normal shutdown and an emergency trip?
For a normal planned shutdown, the sequence is important. First, you stop the flow of the process gas, the cold LNG vapor. Then you close the main steam supply valve. But there's a crucial detail.
Which is?
You need to leave the steam flowing for a short period after the cold gas flow is stopped.
That seems backwards. Why keep heating if you're done?
It's to prevent the unit from freezing internally or suffering condensation damage as it cools down. The residual cold from the process gas needs to be gently purged by the remaining steam flow before you fully isolate the heat. It avoids cold spots and potential ice formation inside.
Okay. In an emergency trip, that sounds much more abrupt.
Oh, it was immediate and automated. It overrides any operator input to shut things down instantly and safely isolate the unit. There are several conditions that will trigger a trip signal.
What are the main ones?
The key ones you typically see are a high condensate level in that drains tank, which could mean it's not draining properly, maybe a blockage. Then there's low condensate temperature. This is critical. It means you don't have enough steam flow, and there's an immediate risk of the cold gas freezing the tubes.
Which we know is very bad.
Very bad. And of course, the other big one is high gas outlet temperature. If that split range control fails or something else goes wrong and the outlet temperature spikes up, say it hits plus 100 C as a trip point.
It shuts down immediately.
Instantly. The trip signal does several things, but crucially, it forces the output of that PID temperature controller straight to 0%.
And what does 0% controller output mean for those split-range valves?
It means the valve letting gas into the heater slams shut 0% open, and simultaneously, the bypass valve is forced fully open, 100% open.
So heat source instantly removed and the cold gas flow is immediately diverted away from the heater entirely.
Exactly. Maximal isolation, maximal safety response. And importantly, the controller is usually locked into manual mode after a trip. The operator has to go to the control system workstation, acknowledge the trip, understand what happened, and deliberately reset it before they can even think about restarting. It forces investigation.
Right. So we've really dug into these gas heaters, where they're called HD, boil-off, or fuel gas types.
Yeah.
They're clearly much more than simple heat exchangers. They're specialized pressure vessels acting as this really critical, carefully managed bridge.
A bridge between the extreme cold of the cargo and the operational needs of the ship. And as we've seen, so much of the design and procedure is focused on safety, on maintaining control within very specific limits.
Especially that non-negotiable plus 80 degrees Celsius limit during the tank warming operations. That seems to be the absolute red line.
It really is. And all the layers we talked about, the atmospheric checks in the machinery room, the mandatory steam preheating, that dynamic split range control trying to balance hot and cold flows, and the constant monitoring of the condensate for leaks, it all highlights just how complex it is to handle methane safely on a ship at sea. It's a whole network of interacting safety systems.
Okay, so pulling this all together for you, the learner, we've seen this robust system with trips designed to shut off heat immediately. if things go wrong, like if the condensate gets too cold, signaling a lack of steam. So here's something to think about. The low condensate temperature trip is there to prevent freezing if steam flow is insufficient. But consider this. What kind of operational failure, maybe involving a sudden and sustained loss of steam pressure upstream, could potentially allow cold gas to keep flowing through the heater, maybe even fooling or bypassing that temperature trip long enough to cause the very damaged severe metal stress or freezing that the preheating and trips are designed to prevent? Chew on that as you continue your deep dive into